delete, delete, delete anything that you see. Maybe I shouldn't say anything that you see, but any of the points that are there. Check in your groups real quick. Did they get it done?
Yes.
All right. Here we go. So you guys have already taken these 2 pages of notes for anyone joining us. Hi, Joyce. Hope the graduation went well. But other than that, say hi to Caroline and Andrew. You have in your y equals 3x minus 2, you have your table set up on ask. And then in your table, you've deleted out any points. You've deleted out any points. All right, here we go. Section 12.1, limits. Usually, I do this whole preview to calculus, but I might just wait and do it on Monday. You guys wouldn't have needed to take notes on it. Let's just introduce this called a limit. This thing is called a limit. The informal definition, and you're like, informal, it's a whole paragraph. Yeah. It's informal mathematically speaking. The formal one is way crazier and has all these Greek letters of epsilons and deltas and proofs and all this stuff. So we'll just say this is like the simple version. The simple version says, if f becomes arbitrarily close, arbitrary, close to a single number L as x approaches a from either side, the limit of f of x as x approaches a is L. But guess what? In some ways, there are a couple details that are missing, but in some ways, most of this paragraph is represented in this little phrase right here. No, that's good. So this whole paragraph, there are a couple details missing once we shortcut the notation, but this is kind of summarized in the limit of f of x as x, guys, what's the arrow mean?
Approaching.
Good. Approaches a is L, as long as the limit exists. Or another way of saying that, we can almost make it even shorter and say, hey, f of x approaches L as x approaches a. Or we can go to this notation that I showed you very, 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 very briefly with sequences in series. LIM, which stands for?
Limit.
The limit of f of x as x approaches a is L. This one little phrase basically, minus a couple details, encapsulates all of this that you wrote up above. Now, what does it mean? Well, let me try to show you. Over here. If we were to find a limit numerically, which means using a table, we would examine the values of f of x. Wait a minute, hold on, f of x. So f of x is approaching L. Doesn't that mean that these guys must be y values then? If f of x is a y value, then L must be a y value too? And if x is an x value, well, that's kind of obvious, then a must be an x value also? So really quickly, a is an x value, and L is a y value. Something to keep straight. So what we're trying to answer is a y value, is a height value. We're trying to ask ourselves, is there a special y that the function seems to be approaching as the x's seem to be approaching the special x value a? So here's the dealio. If we're going to use our table, and we want x to become closer and closer and closer, what's a mathematical term for becoming closer and closer and closer? Approaching. Good. What's the notation for approaching? Arrow. Good. As x becomes closer and closer to the number it's approaching, or as x approaches a, well, hold on. We need closer and closer to a. But here's the dilemma. X can approach A. X can get closer and closer to A from two different directions, either from below or from above. So X can approach A from below, but X can also approach A from above. And so we're going to need to plug in different X values that get closer and closer and closer and closer to A, from below, closer and closer and closer and closer to A, from above. And what we're going to be doing is asking ourselves the question, hey, what are the Y's approaching? What are the Y's approaching? And are they in agreement? Are they in agreement? If they're in agreement, good, there's an answer. If they're not in agreement, doesn't exist. If they're in agreement, good, there's an answer. If they're not in agreement, it doesn't exist. If you guys want to think about it this way, have you ever heard of votes that needed to be unanimous? Like on a committee or in a group, votes that need to be unanimous? Sometimes, like some of your churches, maybe they have like a deacon board or an elder board. That might be a place where the vote needs to be unanimous. But there are other places where votes need to be unanimous as well. What does that mean if it's unanimous? Everyone agrees. What if one person disagrees? Hey, what about the courtroom? Hung juries? What's going on? Has to be unanimous. Which is why there's a lot of debating, and the jury can be back there for hours and even possibly even longer than that. So a hung jury would be one where you can't get someone convinced. So yeah, we can go into that. But pause, come back. So let's think of it this way. Has to be unanimous, meaning from both directions has to agree. If one direction doesn't agree, fine, doesn't exist. Doesn't exist. Think of it that way. If it's not unanimous, doesn't go. Doesn't pass. Now here's the dealio. I had you guys in your calculator put in 3x minus 2. And here's the reason why. We're going to use a table to try to figure out what this limit is. So the limit as x approaches 2 of the function 3x minus 2. Or I could have said the limit of 3x minus 2 as x approaches 2 is, well, I don't know. But there will be an answer, and I'll put in what it is if I can tell in plug that as x approaches, hold on, who's the a in this problem? What's x approaching?
X is approaching 2.
So I'm going to put a 2 in the very middle. I'm going to put a 2 in the very middle. But the point is not, or a limit does not, ask the question, what's going on at 2? That's not what a limit asks. That's not what a limit needs to be answered by. It's not about what's going on at 2. It's about what's going on as we get closer and closer and closer to 2. So hold on. I want you guys to think about if you were getting closer to 2, but getting arbitrarily close, meaning like so close, you're basically there. Would you be starting at like negative 10? No, I need to get so close to 2 that I'm basically there. How about negative 5? It's better. How about negative 1? It's better. How about 1.9? Oh. So if I start at 1.9, kiddos, how do I get even closer trying to approach arbitrarily close? 1.99. How do we get even closer? Now, do you see how we could keep on doing this? 1.99999999999. I think that's getting arbitrarily close. Like for all practical purposes, close enough. Oh gosh. How do I approach the other side? Start at 100? I mean, start at 50, start at 10, start at 5. 2.1 sounds good. How do you get even closer though?
2.11.
Ah, 1 actually goes a little bit this way.
Oh,
2. Does that make sense?
Oh my goodness.
And 2.001. 2.000. Okay, we're getting arbitrarily close. Okay. Ready? Go. Type in 1.9. Type in 1.99. Type in 1.999. If you want to go super crazy, see how many 9s you can fit before the calculator says, I can't do it, I'll round it. We don't want it to be rounded. You guys know what I'm asking?
Yes.
Who figured out how many 9s we can do before it rounds? 4. Oh, that's lame. Why 4? Check out your little box. There's only so much space. If you go one more 9, it's going to be like 2. Well, hold on, wait. It does say 2, but what happens if you go back up? Oh. So actually, you could still have 1.99999 until this window maxes out. How many 9s will that be? Well, you just can't have it go beyond the window, I don't think. How many 9s? Oh, nope, that's not going to be good.
Yeah, you can go beyond the window.
At one point, though, it will round.
It just still does.
Oh, it still does it. You did 13 and it still kept it?
Just kept pressing it.
Nice. Okay, well, the other day it was rounding weird. Pause. So it stores all these 9. So here's the question. Did f of x, if we're still approaching, we're not at 2, we're just getting closer and closer and closer to 2, did the y's actually get to 4? Because it looks like it's approaching 4, right, the y's?
Getting closer.
F of x seems to be approaching. Oh. Here's the problem. At some point, the calculator, even though it shows the 1 point, it said forget it, and it plugged in 2. So be careful. There actually are only so many 9s. Now here's the dealio, guys. Do we really need to type in all those crazy 9s?
No.
No, because what can we already see? What's going on?
Approaching.
We can see the 4. There we go. See, it's gonna keep going until this maxes out, and as soon as this goes beyond, it'll round to 4. So that's what I meant by maxing out. So I could plug in the 3.7. I could plug in the 3.97. I could plug in the 3.997. I'm not going to plug anything into there because, to be honest, the at 2 really doesn't matter for limits. It matters for something that we would call continuity of a function, but for limits, it does not matter. We're just looking at the approach. So guys, as the approach happens, what do my y's seem to be approaching
4.
as x approaches a? 4. Now wait, hold on. That's only from below. Okay, struggle. From below, f of x seems to be approaching 4. The struggle is, I said if it's not unanimous, can we put the answer? No. So let's go from above. Can you guys plug in 2.1, 2.01, 2.001 if you want to have tons of fun? 2.000. Or do the y's seem to be approaching? Someone give me the value for 2.1. 4.3. How about 2.01? 4.03. Is it 4.003? What seems to be happening from above? The y's seem to be approaching
4.
now. Is it unanimous?
Yes.
So therefore the is 4. Dun 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 dun. Does it make sense?
Yeah.
Now, if you did plug in 2, did anybody just plug in 2? If you do plug in 2, what do you get? 4. Oh, that's interesting. Maybe that would have been shorter, but pause, I said. A limit is not about what's going on at A. It's all about the approach. It's all about the approach. Just trust me, that's important. So what if, well, okay. You don't need to write any of these down. It's basically that there are lots of different illustrations for limits. Repeating decimals is an example of a limit in the sense that we can never write out the full decimal equivalent of 1/6. We never could write it out. We can write ... to say it goes on forever. We could do like an infinite sum with an infinity and like the summation and write it out with like a sub 1 and with r and all that jazz like we did in geometric sequences. But we could never actually write all of these. We would have to just say, there's infinitely many converging to, it's limited by 1/6. 1/6 holds in that infinite decimal. We talked about when we were doing the geometric sequences in series, we talked about how M.C. Escher, the guy who did all these up here, how he liked to show geometric representations of different mathematical concepts. And so the idea is, I can count these fishes. Oh, it's getting harder, it's getting harder, it's getting harder, because as these fishes get smaller, how many, or what happens to the number of fishes? It goes up. But here's the idea. Even though the number of fishes are approaching infinity, isn't this still bounded in a finite space? Interesting. The infinite bounded in the finite. There's this whole thing called a fractal. Those are super crazy. It's the math, not the new math, but it was repurposed in the 70s that basically led to allowing CGI to become what it is today. So that's kind of cool. Go look at a Nova documentary about fractals. It was basically first used, I think, in the Star Wars. The originals, well, episodes 4 anyway. When the lava was like coming. Yeah. Anyway. That was pretty crazy in the sense of it wouldn't have been possible without this guy talking about fractals and this computer animator basically being like, wait a minute, I could use that to make this more realistic, and then it just all blew up and went crazy, and now things are what they are today. Coming back. So, even though there are lots of cool applications to the idea of a limit and lots of cool ways that they've been used, let's come back to this limit, which is the foundation of basically all the study of calculus, or what made calculus possible. I want you guys to remember, it's not about what's going on at A. It's all about the approach. We already did that problem. We already got there. Let's go to a new example. What if we were to go ahead and pick out this guy? So this is the one we just did. We plugged in, chugged. We actually didn't really care what was going on at 2. We just asked what was going on from either side. We haven't really gotten to the graphs quite yet, but we're working with the tables still. I want you guys to do the exact same thing with this function in this limit as x approaches this a. So write down the example, then go to your calculator and change it up. Function's different. Your a is different, so numbers you're using to approach are different. So change the y equals, go into your table, delete, and then think about, wait, I'm headed towards a different a. And as you guys do that, I'm going to set up my table. You have to change your y equals. You have to put a different number that we're trying to approach. It's -3 in case you guys can't see it. It's kind of small. Be thinking, how would I approach -3? Remember? It's all about the a. X approaches -3 of x plus 3 over x squared minus 9. From below, oops, if I can spell below. And from above. From below and from above. To help us out, I'm going to do a little number line because some of you will get kind of confused as to what numbers to use for from below and from above. Think, getting in really close to -3 from below, really close to -3 from above. Now pause. That's a good one, but where does it go? From below or from above?
That's from above.
Good. A lot of people would have said from below without thinking about it, because 2.9, oh, it's lower. Wait. On a number line, -2.9 is actually
A bit greater.
above, a little bit higher. Good, so from above, -2.9, -2.99, -2.999. Someone give me the decimal for -2.9.
Negative 10.7.
10.7? How about for -2.99?
Negative 2.99. Negative 10.97. So then it'd be negative 10.997.
Ooh, does that kind of look like it's going, the function's going to -11-ish? How would I come from the other direction?
4.0.
-3. Ooh, don't go -4 point.
Oops.
Right? Go 3 point.
0.01.
And then -3 point.
0.001.
Now guys, this whole thing is not about whether or not you can learn to solve these eventually with tables in your graphing calculator. Eventually, we don't want the calculator anywhere near us when we're solving these. But I need to cement in your guys' brains that a limit is all about the approach. Getting closer and closer and closer from either side, needing it to be unanimous. Michael. Okay, the reason you're getting fractions is because you're using the cool little alpha y equals, which is really good, except for this one case. So go back to your y equals, put parentheses, and a division sign. Sorry, once you use that, it's like, oh, I can use it from now on. And you're like, no, I need the decimals. So yeah, go back and do the parentheses and do the division. Sadly, there's no other real way to do it that I know of. Noah?
Where did the -10.7 come from?
Oh, because remember, people are putting in their graphing calculators, and I just haven't modeled it, they're putting this new function in now. And as Michael just said, the alpha y equals gets kind of messy in this one, so I'll put it in this way, but they're putting the x plus 3 all divided by Oh, I need my parenthesis. Don't forget your parentheses. It'll get all messed up. I need the numerator grouped and the denominator grouped. X squared minus 9. And then they're going to their table, but they cleared out the old one because we're not approaching 2 anymore. Now we're approaching negative 3. And so to do that, they started approaching from above, and I was like, sure, why not? That's fine. So then they were plugging in. Does that make sense, Noah? Yeah. What's the problem, though? Chris, what happened? I think you messed up how you typed it in, bud.
What?
Because what do I see it approaching?
Chris, you are wrong.
Does anybody else agree with me?
Yeah, I have it.
Yes.
Yeah, it's like
Oh.
negative 0.16.
Good. Wait a minute. Didn't we just see the 0.166666666 thing?
Whoa. Wait, what's going on?
What is going on?
I don't know. Maybe you typed it in wrong. Did you do the parentheses? If you did the division? Or did you do x squared minus 9? Did you do positive 2.9?
No, I did negative.
Yes. I'm getting. Yeah, I got that.
Didn't we just look? What is 0.16666666666? It's the fraction.
Unsolved.
No. It's a fraction. We just saw it. You didn't notice it with the whole MC Escher and the fractals and all that? Probably not. What decimal is that?
Repeating.
Yeah. What's it equal? Okay. So it seems like we're approaching negative 0.166666666, which would be negative 1/6. There we go. Somebody who plugged in and got this for the negative 2.9, negative 2.99, etc. What'd you get for negative 3.1? 0.164? 39. Then negative 0.1664, and then negative 0.16. Hey! Guess what? Unanimous? Yes. So therefore I can say the limit as x approaches negative 3 of my x plus 3 over x squared minus 9 does seem to be negative 1/6. Now guys, last table, let me move this page so we can see it because I put my little MC Escher thing in there. What the graphing calculator table told us, 4 actually showed up if we plugged in 2. At 2, there was a point at 4, so technically if we had just plugged in 2, we would have gotten the answer of 4. Now, hold on, let's see what's going on with this guy. What happens, guys, if you plug in negative 3? Even though it's technically not what a limit is about, last time when you plugged in, it actually ended up being the answer. So what happens if you plug in negative 3 now? Error. Wait a minute, I don't get it. It doesn't match exactly, which is why we don't look there. It doesn't always match. Sometimes it will and sometimes it won't. And maybe there's a shortcut to solving that's coming. But for the idea of a limit, the idea of needing to approach negative 3 and see what the y's are approaching, it's not about what's going on at negative 3. It's about what's going on from below or above negative 3. And did the approach from below and from above agree? Yes. So did the limit exist? Yes. Guess when, my Mean Girl fans, guess when the limit does not exist? No, when she was looking at a cute boy in class and then someone else had already gotten the wrong answer in the competition. But coming back, it was random. She did absolutely no math. She guessed, and anyway, it was kind of annoying from a mathematical perspective. But coming back, she totally guessed. But coming back, in calculus we solved that limit. It's kind of funny. And we're like, she could not have, no, there's no way. When does the limit not exist? If they're not unanimous. If they disagree. But so far they've been in agreement. Just if they ever do disagree, we'll have to say the limit does not exist, DNE, and be done. So whether the point is filled in or whether the point is a hole. Interesting. The limit will exist. Now, kiddos, we're going to end with this page right here today. We're going to continue and finish up section 12.1 on Monday, but a lot of you could probably do the majority of homework. I'd say at least half of it with what we've done. Let's go ahead and write down this second one. The first one was numerically using a table in your graphing calculator. The second one says we can actually do this looking at a graph. The table was very, very, very important, I think, for your brains being like, okay, it's not about the 2, it's about the 1.9 and the 2.001. It wasn't about the negative 3, it was about the negative 2.99999. Oh, that was from above. Negative 99999 and the negative 3.001. It's about the approach. But ultimately, it's going to be more helpful if we can actually pull you out of the table, taking that foundation and saying, okay, so how do we think about this on a graph? We've already talked about with a limit, of a certain function, which, to be honest, I don't even know who this guy is. I'm just going to call him f of x. The limit of a certain function as x approaches, well, according to the graph, they show me these little arrows, so I'm pretty sure they're trying to tell me x is approaching 1. So that's why I fill in that notation. I'm trying to ask myself the question for the limit, what do the y's seem to be approaching? So if you guys look down here, x is approaching 1 from below and from above. And what are they trying to show me right here? The y's seem to be approaching 2. Out of this graph, I can technically make this statement. For the answer to a limit problem, we're actually looking up at the heights. We're looking at the y values. Because remember, the L to a limit is a y value. As x approaches, what are the y's approaching? So if you go to this x and you go up to the curve, if you go to this x and go up to the curve, if you go up to this x and go up to the curve, okay, do the y's seem to be, as I get closer and closer and closer and closer, approaching anything? Yeah, 2. As I go up to the curve, and as I go up to the curve, and as I go up to the curve, and as I get infinitesimally close, 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 what do the y's seem to be approaching? 2. Am I looking what's going on at 1? No. Now Monday I'll develop further the idea of coming from below and above. I'll make one of them a different color, like maybe something like red. I'll put a little guy in a little car and he'll be driving, and then I'll put on the other side something like green. I'll put a guy in a car and he's driving. And we'll talk about this thing with these diners saying, they're both trying to go have breakfast. The limit will only exist if they're headed to the same location. But if they get out of their cars and if they walk up to the diner and if they go to pull open the door and it's locked, it's a family business. They decided to take today off. Are they getting breakfast? The answer is no. But did they meet? Basically. Were they going to the same place? Yes. They might just not get breakfast. And that's an example of this one. Headed to the same place, but they're not getting breakfast. The point's not there. But that's okay. The limit still exists. They were headed to the same place. They approached the same location. This one over here, they are getting breakfast. Why? They're approaching the same location. They're going up, and when you plug in 2, you get out 4. It all works. Everything goes together. It's a continuous function. What the intent was what was actually fulfilled or what actually came true. This one, what the intent was, what they were trying to approach, they'll never actually get to. Anyway, we'll get back to that a little bit more on Monday. For those of you guys that pretty much have your corrections done, guess what? Get in your homework spiral. Section 12.1, I'll put up section 12.1 in just a second. You can start on homework. For those of you guys that are like, ooh, yeah, I have corrections to do, grab them out. I can answer questions. Your classmates, your group members can answer questions to help you out with homework this weekend. Sound good? We have 10 minutes. Everybody got back there?